Hello and good day. Today on part 221, we'll be discussing Spearman's rank correlation. It is found it is it was found that there are difficulties in quantifying a data or a set of data that has big values. Rank correlation is used to determine the extent to which the variables are correlated. This idea was employed by Spearman's rank correlation. If you remember in our previous sessions, we said some data sets tend to have extreme values that pose as outliers that affect the accuracy or computation of those values using the Pearson's correlation coefficient. So here the Spearman has come to address the issue of extreme or large values. This idea was employed by the Spearman's rank coefficient, and it assumes that the data to be at least an interval scale kind of data. That's the assumption. Charles Spearman, a British statistician, introduced a measure of correlation for ordinal level data known as Spearman's rank order correlation coefficient. A measure of the relationship between two sets of ranked data is what Spearman correlation measures, and it is represented by RS, and it ranges the values of the Spearman's rank correlation coefficient ranges from -1 to +1. Zero correlation, as in the previous cases of correlation, indicates no correlation at all. At the end of this lecture, you are expected to be able to explain the Spearman's rank correlation, describe the computation of rank correlation coefficient, and apply the concept of correlation in administrative decisions. The Spearman correlation coefficient, which is RS, is called the Spearman's rho, or the Spearman's rank order correlation. It is a non-parametric measure of correlation used to assess the strength and direction of relationship between two variables. Explaining further on the concept of Spearman's rank correlation. Unlike the Pearson's correlation, Spearman's correlation does not require the assumption of linear relationship between variables. Instead, it assesses the monotonic relationship, which is either a consistently increasing or decreasing pattern. Spearman's rank correlation is particularly useful when dealing with ordinal or ranked data, where the actual numerical values may not carry meaningful information. It involves ranking, which means arranging a set of variables or dataset in ascending or descending order. Order matters here, but the relative order of the data points is important, of course. For example, if we have ranked data on students' academic performance, like the first, second, and third place, and their study hours, Spearman's correlation can be used to evaluate the relationship between these two variables. The calculation involves the following steps. First, you rank the data, then you calculate the differences between the ranks. Let's say you have X and Y. After obtaining the ranks of X, that is arranging them in ascending or descending order and giving them labels of numbers representing which one comes first. That's what ranking is about. You go ahead to calculate the difference in the ranks. You subtract the rank of Y from the rank of X. You square the differences, and then you go ahead to calculate the Spearman's correlation coefficient. The formula is given as seen. In your computations, what your formula demands are the preparatory computations that you must do. And after doing your preliminary computations, what's left is for you to substitute into the formula. In the formula demands that we get the square of the differences in ranks and also the number of observations. That's all you need to compute the Spearman's correlation coefficient. So your preliminary computations should involve ranking, getting the difference in ranks, and then the squares of these differences, and then the summation of it all. Then you go ahead and do your substitution. Like other approaches we considered earlier in correlation, a value of +1 indicates a perfect positive monotonic correlation. A value of -1 indicates a perfect negative monotonic correlation, and 0 indicates no monotonic correlation. Spearman's correlation is robust to outliers and can handle skewed data. You remember earlier I explained outliers as observations that differ significantly from the rest of the population or from the rest of the observations in a data set. They are extreme values that are either too high or too low compared to the rest of the members of a data set. The Spearman correlation is not affected by such values. That's why it's referred to as being robust. It is resistant to extreme values and it can handle a skewed data. A skewed data refers to a distribution where data points are not evenly distributed around the mean. Normally, the approaches considered before now are affected by such conditions except under certain assumptions, but the Spearman correlation is resistant to outliers and can handle skewed data in its computation. This makes it a valuable tool in situations where the assumptions of parametric methods like Pearson's correlation are not met. Yes, it kind of covers the inadequacies of the Pearson's correlation coefficient, where from the formula where n is the value of the data set, d is the difference in ranks assigned to x and y. Note that when computing the Spearman's correlation coefficient, there are problems or exercises that the ranks are given from onset. The ranks are given in the question, and there are some where the ranks are not given. Only values of x and y will be given for you to compute the ranks. So you have to put that into consideration. You cannot go ahead to begin to find the difference in ranks from the values of x and y. You have to arrange them according to ranks, and then you find the difference in ranks, except if given as ranks from onset. When ranks are not given in a problem, you are expected to do the ranking in ascending or descending order before computation. When ranking the variable and you find out that a particular variable appears twice, we have a list of numbers. We have 1, 2, 3, 4, 5, and 4 again. Instead of 6, we have two 4s in this data set. So 4 appearing twice in this data set is called a tie. We say there is a tie. In this situation, the rank to be assigned to each of the values should be the mean rank of the two numbers. For instance, if the ranks are positioned at 3 and 4, the rank to be assigned to each of them will be the sum of the ranks, which is 3 and 4, divided by 2, having 3.5. So wherever you see that particular value that repeats, it will take the rank of 3.5. You understand that more when we come to numerical illustrations. Let's consider this particular one. It says ranks are given to 5 contestants during a beauty contest by 2 judges, X and Y, as shown in this table. So this is basically the question, and we were directly given the ranks. As you can see, this wasn't labeled X and Y. It was labeled rank of X and rank of Y. So it means the ranking had been done from the question. There is no need to compute, to assign ranks to these numbers. They are already ranks given. So you just go ahead and look for the difference in ranks and then the square of those differences. So the question went ahead to say, compute the Spearman's rank correlation coefficient. And what does the formula of the Spearman correlation coefficient demand of us? The difference in ranks and the number of variables. The number of variables is 1, 2, 3, 4, 5. So our n is 5. And then going to look for the difference in ranks. The difference in rank simply means rank of x minus rank of y. 2 minus 1, we have 1. 5 minus 3, we have 2, and so on. After obtaining the difference in ranks, then you go ahead to square these differences. After squaring the differences, remember the formula for the computation of the Spearman seeks that we substitute the sum of the squared differences. So getting the squared differences is not enough. What we need now is the sum of all these squared differences. And by the representation on this table, we can see that adding them up, we have 10. 1 plus 4 plus 1 plus 4. We have 10 as the summation of di squared. So you simply come to your formula and you substitute this summation of di squared with 10. This 6 is multiplying them all. So it will be 6 times 10 divided by our n, as we counted, is 5, divided by 5 into bracket 5 squared minus 1. So that's all you need. To make it organized and neatly presented, it is advisable to arrange and get compute your difference in ranks in a table before proceeding to substituting into the formula. Now, substituting into the formula, we have this, and when you compute this with the help of your calculator, you arrive at 0.5, which is approximately 1 mathematically. And 1 in the interpretation of the Spearman's correlation coefficient indicates a strong relationship between George's X, between the judgment of George X and George Y. So you can conclude that there is a strong relationship between their judgments. That's the conclusion from this particular result. Considering another illustration, you can see that in this particular one, the ranks were not given. They were only given as x and y. So it is your duty to calculate the ranks and to assign ranks to these numbers. So assigning the ranks to x and y, we arrived at rank of x and rank of y. What we need for our computation is the ranks, not the values of x and y. Now, having the ranks, we look for the differences in ranks. Rank of x minus rank of y gives us di. That's the difference in ranks. Now, the square of these differences is what we have as di squared. Then the sum of these squared differences is what we have as 95.5. So going to substitute into the formula like we did in our first illustration, we have this, and then the resulting answer is minus 0.7054. It is very important to indicate your conclusion. You have to indicate your conclusion because this means something. If you have a positive R value, it means something. If you have a negative R value, it also means something. And if you have 0 as your R value, it also means something. So your conclusion counts. In this case, we have a negative R value. So we conclude that there is a strong negative relationship between variables x and y. As we explained earlier, this means that as one variable is increasing, the other is decreasing. Going to the third illustration, this is about prices of foodstuffs from 8 different markets collected by a researcher as shown in the table, and we're asked to find the rank correlation coefficient as to how the prices of these different commodities are related. Here is the table. The prices of millet, maize and sorghum in mudu per measure, and then in different markets, market A, B, C up to H. Then we have the prices as represented in different markets. We go ahead to find the correlation between the various foodstuffs. We will need to start by finding the ranks. Remember, you were only given the prices, not the ranks of the prices. You can go ahead to begin to find the difference in rank from this data set given. So you assign ranks to these prices either in ascending or descending order. You assign ranks to them and then get the difference in ranks and then get the square of the differences. The rank of prices of millet, we have it as shown in the first row, the rank of maize in the second row, the rank of sorghum in the third row. Now, we have to find the relationship between millet and maize, the relationship between millet and sorghum, and the relationship between maize and sorghum. And in order to do that, we need the rank differences. So the difference in rank between millet and maize is as shown. That's subtracting the ranks, that's the difference between the ranks of millet and the rank of maize. 1 minus 1 gives you 0, 4 minus 2 gives you 2, 2.5 minus 5 gives you minus 0.5. So that's how it goes. Oh, 2.5 minus 3 is the difference between millet and maize we are considering. 2.5 minus 3 gives you minus 0.5, and it goes on and on. That's the rank difference between millet and maize. Then you go ahead to find the rank difference between millet and sorghum. That will mean 1 minus 1, 4 minus 7, 2.5 minus 5, and that gives us this. And then the rank difference between maize and sorghum, which will mean 1 minus 1, 2 minus 7, 3 minus 5, and then that gave us this column. These are the differences. Then these columns, the last 3 columns, are the squares of these differences. Then the last 3 rows gives us the squares of the differences. Then this particular column gives us the total of the squared differences of between millet and maize, millet and sorghum, and maize and sorghum. These are the things we need to substitute into our formula. So by this table, we are halfway into our solution. What's left now is the substitution and the use of your calculator. To check the relationship between millet and maize, you substitute the difference in rank between millet and maize, and you arrive at this. To check the relationship between millet and sorghum, you substitute the square of the differences in ranks between millet and sorghum, and you have this. And then the one between maize and sorghum, you arrive at this. So drawing our conclusions based on the values, the relationship between the prices of millet and maize is very strong. Millet and maize, that's the one that has 0.8, which is approximately 1, and a Spearman correlation coefficient of +1 indicates a strong relationship. So that will be our conclusion for the relationship between millet and maize. For the relationship between millet and sorghum, we can say there is a weak relationship, and also for that of maize and sorghum, there is a weak relationship because it is less than 1. Even though it is positive, it is less than 1. So there is a weak relationship between their prices. That's the conclusion that can be drawn from this data set. With this, we'll be wrapping up on Spearman's correlation coefficients. Thank you.